Hello and welcome back to Hello Maths. Today we're going to be looking at this problem here. We're going to be proving that the two diagonals meet in the centre of the square. Now this might feel pretty obvious, and there's lots and lots of great ways to prove this, but we're going to prove this using vector geometry because it ends up being a really nice intro into some of the more complicated techniques that you use when dealing with harder vector geometry questions. And this comes up actually in A-level maths as well. So let's start with our shape, our square, and let's label the vertices. So we've got O here. That is usually how we label the bottom left of a shape because it's like the origin. And then let's call this A, B, and C. And we're going to use capital letters for our vertices. And to define our vectors, this one here, we're going to use lowercase a. This one here, we're going to use lowercase b. You could have used any letters here, but it's nice to use capitals for the vertices and lowercase letters, usually maybe they might be bolder than the other ones for our vectors, lowercase letters. So now what we care about are these two diagonals here, which I've drawn pretty badly, but you can see we want to prove that they meet at this point here, x, and we want to show that they meet at the middle. And the way we're going to show that is we're going to show that this is half and half of the diagonal, and similarly this is half and this is half. So we're going to show that those diagonals bisect each other, which means they cut them into half. And the way we're going to do that is by defining the journey OX in two different ways and then equating those two ways together, because how we get from O to X has to be the same. So let's see. Root 1, we're going to look at just straight up this journey here, this journey. And what that journey is, it's some amount, we're going to use the Greek letter mu here, it's some amount of OB. Now we're trying to prove that it's half of it, but for now we're going to imagine that we don't know that it's just mu. So in fact I'm going to get rid of these halves. So what we do know is that OX is some amount of this longer diagonal OB. And actually we can define OB as well, because OB is just OA plus AB. We've gone from O to A and then from A to B. O to A is the vector B and AB is the vector A. So there we go, we've defined that journey. Which means that OX, one way of writing it, is some amount of A plus B. Could have also been B plus A, doesn't matter. It's commutative, doesn't matter the way I do my addition. Okay, what other root shall I use? How about let's go from O to A and then from A to X. So here I've got that OX is also OA plus some other amount. Now we are trying to prove that it's going to be half, but we don't know, so let's use another Greek letter. Let's use lambda, some amount of AC. This last section from A to X, we don't know what it is, but we do know it's some amount of AC. And let's define our bits in there. OA is just B, and AC is just A minus B, because I've gone from A to B, which is A, but then from B to C, which is minus B, because remember, direction matters with vectors. So that means that OX can be written as B plus some amount of A minus B. And now we come to the important step, where we're going to equate these two things together. Whatever happens, this OX here, this journey here, has to be the same as this journey here, because the vector OX always describes the journey from O to X. So we know that those two parts, this one and this one, have to be identical, because they both define the exact same journey. So we can equate them, we can make them equal to each other. So we have mu lots of A plus B is exactly the same. I'm going to use those three lines here to show they are always the same as B plus lambda A minus B. Remember what we've done is we've defined OX in two different ways and we've equated them to each other. So we've got mu A plus mu B, which is exactly the same as B plus lambda A minus lambda B. And now we're going to use a method called equating coefficients, where we're going to look at the coefficients of A and B. And because we know these things are equal to each other, the left-hand side and the right-hand side, the coefficients of A and B have to be the same. So if we look at A, we have that this coefficient here has to be the same as this coefficient here, because those are the only A's on either side. So we have our first fact. Mu has to be equal to lambda, which is good. Because remember, we have that OX is some amount of OB, and AX is some amount of AC. And we've shown straight away that they're the same, that lambda is mu. Now we need to find what they are. So on this side, what we can actually do is factorize out the b's. So we have 1 minus lambda b's plus lambda a. And now looking at the coefficients of b on the left-hand side and the right-hand side, we've got that lambda here has to be the same as 1 minus, sorry, mu on the left-hand side has to be the same as 1 minus lambda on the right-hand side. So that's my second equation. Equation number 1, equation number 2. Mu equals 1 minus lambda. Now we can solve this simultaneously. We can just substitute 1 into 2. We have that mu is equal to 1 minus mu. So, they're actually lambdas. Lambda equals 1 minus lambda. 2 lambda equals to 1. So lambda equals a half. Similarly, that means that mu is a half. And there we go. We've got to our answer. We've got that OX is equal to half of of OB, of that long diagonal. Similarly, AX is half of AC. If those smaller journeys are halfway of those longer diagonals, then those two lines must bisect each other, which means that this point must be exactly in the middle. So what we've done there is we've shown that the longest diagonals in a square meet at the centre. And obviously we've done it in quite a convoluted way, but actually this method is going to be very, very useful when we're dealing with trickier shapes. So what you can do is try the exact same thing, but with a parallelogram or with a rectangle. And you'll find that the exact same method will work for that too. And I'm going to link to a similar question that uses this method in the description below. Thank you very much for watching.